For our physics final project, we decided to research the physics of bowling. As any sport, bowling has a history that dates far back to ancient times. Over the years, the game has evolved to the version that we know it to be today. However, the game was first created and played by the Egyptians, or so we think. In the early 1900s, an English anthropologist named Sir Flinders Petrie discovered what appeared to be a crude form of bowling in a child's grave in Egypt. If what he found was in fact an earlier form of bowling, the sport may date back to 3200 BC. Interestingly enough, though, versions of bowling appear to originate from places other than just Egypt. Variations of the sport were brought to the Americas by British, Dutch, and even German settlers, implying that the sport as we know it today is a culmination of each of the different versions introduced throughout the ages. Bowling as we know it today is a sport that involves knocking down an arrangement of 10 pins by gliding a ball across an oiled floor. Typically, the distance between the line that the bowler must release the ball behind and the first pin at the far end of the lane averages about 60 feet, or 18.29 meters. The bowler has 2 chances in each round to knock down all the pins. Professional bowlers typically average about 20 to 22 miles per hour for the speed of the roll, so that by the time that their ball reaches the pins, it will average about 17 to 18 miles per hour. Before we go into the components behind the physics of bowling, I would like to mention that the mass of the bowling ball we used was 3.628 kilograms, and the distance between the foul line and the first pin was 18.28 meters. In our experiment, we used a phone to record the time it took for the ball to reach the pins in order to help us calculate the speed of the ball after release. However, most bowling alleys have radar guns that assist in this. It is also known that bowling alleys average about 60 feet or 18 meters in distance, but if you do not know this, you can use a meter stick in order to help you determine the distance. First, we will look at linear motion.
Linear motion within bowling is apparent. Besides the bowling ball itself moving as it rotates, it is also moving as it rolls down the lane. Since the goal of bowling is to knock down the 10 pins at the end of the lane, the player must roll the ball in a linear line. Not only this, but the ball travels at a constant velocity due to minimal friction from the lane to the bowling ball. Since the ball is being released by an external force, the player, and rolls at a constant velocity from there, linear motion is present. Velocity can be found by the formula V equals delta x over delta t. Essentially, the velocity of the ball depends on the time and the distance from the ball to the pins at any given point. A normal bowling lane is 60 feet long, which is 18.288 meters. Using the change in position from 0 meters from the foul line to 18.288 meters and the time it takes to reach the pins, velocity can be found. For example, for Taylor's strike recorded, the change in time is roughly around 2.69 seconds, and the change in position is 18.288 meters. Plugging the 2 numbers in, the velocity of the ball for the strike is 6.799 meters per second. In terms of acceleration, this depends on the change in velocity over change in time, giving us the equation A equals delta V over delta t. In this case, acceleration is 0. In order to find the displacement from a different point instead of just from the foul line to the pins, the formula used is x equals V initial times delta t plus 1/2 A delta t squared. Since we have the velocity and the acceleration, as well as change in time, we can plug these numbers in and find the displacement from an unknown point to the end of the lane. For example, to find the position of the ball at any given point, we time how long it takes to get to that position and how long it takes to get to the end of the lane. In our case, if we choose the initial time of 1.27 seconds and the final time of 2.69 seconds, we can subtract the initial from the final and find the change in time, which is 1.42 seconds. The initial velocity of the ball, since it is already in motion, is 6.799 meters per second, and our acceleration remains at 0 meters per second squared. The graphs are also in relation. The derivative of the position equation and graph gives you the velocity equation and graph. The derivative of that gives you the acceleration equation and graph. The position equation here is x equals 6.799t. The velocity equation is v equals 6.799, and the acceleration equation is a equals 0.
The next topic that we decided to include in our experiment was impulse and momentum. Momentum is a vector quantity that describes the motion of a moving body. Momentum is a product of an object's mass and velocity. The equation used to calculate momentum is P equals mv, where P is the momentum, m is the mass in kilograms, and v is the velocity. In the example of the bowling ball and pins, momentum can be used to describe the motion of the ball through an allotted time. Impulse is the quantity used to describe the effect of a net force acting on an object. Impulse is the product of an average net force acting on an object multiplied by time. The equation that can be used to calculate impulse is I equals F times delta T, where I is the impulse, F is the force in newtons, and delta T is the change in time in seconds. In our experiment, we were able to find through the equation F equals ma that the force on the bowling ball was about 9.208 newtons, and that delta T was around 2.69 seconds. Once the force and change in time were determined, we were able to multiply these values together to come to our resulting value of about 24.769 newton seconds. The impulse in the bowling situation can be used to describe the force of the person on the bowling ball, as well as the force of the bowling ball when it comes into contact with the pins. While we did not collect data to determine the impulse of the bowling ball on the pins, it could be seen that in another situation, these equations and numbers and such could be used to determine the impulse of the ball on the pins. The collision of the bowling ball on the pins causes the pins, which were at rest, to gain momentum through this sudden force. It can be seen that the change in momentum of an object is equal to the impulse applied to it. This can be shown through the equation I equals delta P, which is also recognized as F times delta T is equal to m times delta V. Since these quantities are proportional, this allows for easy substitution when calculating different values in bowling, such as the force applied to the bowling ball. The sum of two or more objects' mass and velocity is directly proportional to the sum of the object's mass and velocity after the collision. Momentum can be calculated in numerous ways from our real-life experiment, though for this situation we decided to use the equation delta P is equal to m times delta V, seeing that these were the values that were the easiest to obtain. The change in velocity can be determined if we find the velocity right when the ball is released, then subtract that from the final velocity of the ball. Though we cannot calculate an exact value of the momentum because we do not know the initial velocity of the bowling ball, with these equations we were able to apply the physics of impulse and momentum to a real-life situation of bowling.
Next, we will look at the rotational motion of bowling. Rotational motion is the circular movement of an object about its center of rotation, whether that be fixed about another point or simply the center of the object itself. When the ball is first thrown, the ball will glide or slip across the floor before friction of the floor against the surface of the ball allows it to begin rotating. Due to this, the rotational motion of the ball must be considered in two parts: the time that it is slipping and the time that the ball is not slipping. While the ball is slipping, the total energy is equal to the translational kinetic energy, which can be calculated using the equation Ke equals 1/2 mv squared. With the mass of the ball being 3.628 kilograms and the calculated velocity of the ball being about 6.80 meters per second, the calculated total energy came out to be 83.93 joules. However, while the ball is rolling, the total energy can be measured by adding Ke translational and Ke rotational. The equation for that is total energy equals 1/2 mv squared plus 1/2 moment of inertia times omega squared. In order to calculate the inertia of the bowling ball, the equation we needed to use was inertia equals 2/5 times mass of the bowling ball times radius of the bowling ball squared. With our values for mass and radius plugged in, we calculated the inertia to be 0.015 kilograms per meter squared. We then calculated the angular speed by taking our velocity and dividing it by the radius, resulting in an angular speed of 66.93 radians per second. After multiplying 1/2 to those values, Ke rotational turned out to be 33.59 joules. We then added Ke rotational and Ke translational together to find the total energy to be 117.53 joules. Since the total energy must remain the same regardless of whether the ball is slipping or not, due to the fact that the only work being done on the ball is done prior to releasing it, the discrepancy between the two total energy values can only be explained by the fact that we assume that the initial speed of the bowling ball to be 0 meters per second at the moment it reached the ground. However, in order to calculate the actual velocity, we can set our answer we found for the total energy of the ball when it is not slipping equal to 1/2 mv squared and solve for the velocity, as we already know the mass of the ball to be 3.628 kilograms. In doing so, we found the actual velocity of the ball at the instant that it makes contact with the ground to be 8.047 meters per second. With all our new knowledge on the physics of bowling, we decided to go ahead and give it a try ourselves. We met many failures, but we were finally able to nail down the perfect strike.
Woo! Patsy got one! Yeah. Go, Patsy. Yes, Patsy! Ah!
Okay, Zeal.
Go. Oh.
We hope you enjoy it.
Okay.
Physics behind it.
Okay.
Thank you.